In modern digital design, smooth motion feels completely frictionless. It naturally guides the eye and provides immediate feedback. But when that motion breaks, when it stutters and snaps, it disrupts the user's connection to the interface. This comparison illustrates a common failure on the modern web. On the left, a button scales up, but the frame rate plummets to a choppy 24 frames per second. On the right, the exact same interaction holds a stable, fluid 60 frames per second. Both of these buttons are animated using pure CSS. There are no heavy JavaScript libraries or external dependencies involved, yet their performance is night and day. The Royal Research CSS Guide provides the framework for mapping these performance outcomes to the browser's internal rendering logic. A common assumption is that achieving a consistent 60 frames per second is simply a matter of writing cleaner code or reducing the number of moving elements. The actual cause is hardware-specific. High-performance web motion requires writing CSS that intentionally offloads rendering calculations from the central processor to the graphics processing unit, or GPU. Design intent is limited by the underlying rendering architecture. If the browser cannot compute the movement fast enough, the design will never reach the screen as intended. To see how this works, we have to look at the two primary methods for CSS motion. CSS transitions handle the interpolation between two specific states, moving an element from point A to point B. Transitions rely on an event trigger, such as a hover or a click, to start the movement. The browser uses the assigned duration and timing function to calculate the intermediate values required to bridge those two states smoothly. CSS animations function on a separate logic. They govern independent, multi-step sequences that follow a dedicated timeline. Using keyframes, you define exactly how an element should appear at specific percentage intervals along that timeline. The box executes these changes automatically, hitting the 0, 50, and 100% markers without requiring any further user input. While these animations are more efficient than using JavaScript for looping effects, they still require the browser to perform physical work to update the display. Regardless of the method, the browser must draw the result. How it handles that drawing process is where performance is either maintained or lost. When a browser displays a page, it follows a linear pipeline. It parses HTML, calculates styles, determines layout, paints pixels, and finally composites the layers. In the layout phase, the browser calculates the exact geometry and position of every element in the document object model, or DOM. If we change a geometric property, like setting a node's width to 150%, that element expands. Because elements exist in a flow, that expansion physically shoves adjacent elements out of their original positions. Changing properties like width, height, top, or left forces the browser to recalculate the coordinates of every surrounding node. This recursive calculation is called a reflow. Once the layout is recalculated, the browser must then execute a repaint to redraw every affected pixel on the screen. For an animation to appear smooth, this entire layout and paint cycle must happen 60 times every second. This workload consumes the main thread and maxes out the CPU. On mobile hardware, the processor often fails to complete the math before the next frame is due, resulting in stuttering. Animating layout properties is the equivalent of rebuilding an entire structural grid just to move a single component. Efficient motion relies on compositor-only properties, specifically transform and opacity. A transform scale creates the same visual expansion as a width change, but it follows a different internal pathway. Instead of recalculating the layout, the browser detaches the element and places it on its own isolated layer. This enables hardware acceleration. The browser hands this isolated layer directly to the device's GPU. The movement calculations bypass the main processor entirely. The GPU treats this layer as a pre-rendered texture. It can scale or move that texture instantly without affecting the geometry of any other element in the DOM. However, this requires restraint. Applying hardware acceleration to massive sections of a page can overwhelm the GPU's memory, creating new bottlenecks. The most effective use cases are micro-interactions, such as button hover states or form validation queues, where the motion is localized. By manipulating a picture of the element rather than recalculating its math, the browser maintains a fluid frame rate while saving significant compute power. This side-by-side reveals the computational reality. The lagging interaction forces the CPU to recalculate geometry 60 times a second, while the smooth interaction hands that work to the GPU.
Reliable web performance is the result of aligning visual design with the specific rendering mechanics of the browser. Even when using these efficient CSS methods, motion must be used with purpose rather than added for its own sake. Beyond the technical cost, motion impacts how users physically perceive an interface. Rapid or continuous movement can be difficult for users with motion sensitivity to process. To address this, developers use the Prefers Reduced Motion media query. This allows the CSS to detect OS-level accessibility settings and disable animations for users who require a static interface. The Royal Research CSS Guide summarizes these requirements into a final performance checklist. First, default to compositor-only properties. Use transform and opacity to handle movement whenever possible. Second, limit the DOM scope. Isolate animations to the smallest possible nodes to keep memory usage low. Third, respect reduced motion. Ensure the interface remains functional and inclusive by honoring user preferences for less movement. Standardizing these motion patterns as part of the technical architecture ensures the interface stays performant across all hardware.